Sounds good. So Igor, are
Yeah,
you there?
yeah, I'm here.
Okay, so we're going to start up and Igor is going to go through a few more slides. And then the rest of this afternoon is just going to be question and answer, and we will go as long as you want. If you don't have any questions, we'll end very early. And if you have a lot of questions, we will definitely end by 3 p.m. Eastern time. So what happens this afternoon is totally up to the participants here. Tomorrow we have a little bit more structure, but again, we'll have time for more question and answers. So hopefully what you learned today can drive your thinking for what you might want to ask tomorrow as well. So Igor, you want to try to share your slides? Can you do that?
Yeah, I'll try to share my
I think we're on slide
screen.
35, if I'm not mistaken. Yeah, should be
Uh,
35. Perfect.
yes. Can you see it now?
Yep, it looks perfect. Thank you.
Okay. Okay. So these are kind of, I guess, random slides, basically about the configuration, and this starts from topography stuff. So, oops. Let me see. Can you see my cursor? So
yes, we can see.
Yeah, the first, basically the main file related to topography is topo file, which you will be describing in your run deck. I guess Kostas already has shown these parts. So you will be reading a lot of input files, and all of those are sitting in your directory on your computer, which you defined in your model ERC file. And just to make it more like understandable and basically down to earth. So I'm now showing you my terminal screen. Can you see it? Yes. Oh, I hope you can.
Yes, we can see.
Yeah, we can see it.
So basically, let me just go to my home directory, and I will start from scratch. So there is if you followed our instructions, then there is a directory model eSupport in your home directory, and in that directory there are a few subdirectories, and the main one is which we are interested in is prod input files. So if you go there and do ls, well, since I was working with the model for quite a while, I see a lot of input files here. So those are the files which you specify in your run deck, which will be read. And for planetary stuff, of particular interest are the files in planet directory. So here, what I want to show you, we have specific, for example, files for Mars. And that's what we have for Mars. So we have initial conditions, we have topography of Mars, and we have albedo. So just for you to understand what it is. So topo file will be pointing to this file. And I have already opened it in Panoply viewers. I will not do it again, but basically you can just open this file on your Mac. It will automatically start Panoply if it is installed. And here what you see in Panoply window, this is the contents of the file. So those are fractions of different surface type, FGIs, this ground ice, ground fraction, lake fraction, ocean fraction, which is 0 for Mars, height of lakes, latitude, longitude, it's just coordinates, and the atma is the most interesting thing. So if you just, actually I'll have already drawn it, but if I do it again, so if I just double click, oops, what's going on? Why can't I? Oh, I guess it interferes with my, oh.
Maybe you have to share your whole screen, Igor? Is that what you're doing, or are you just sharing the window?
It was just fine working when I shared. But now
I think you have to share your whole screen.
Got stuck.
Uh-oh.
Well, let me just do it that way. Okay, so now I open, oops, I cannot do it again. Sorry, I have to move. It doesn't allow me to click inside the shared window. So just, oop, why? No, it's, sorry. Anyway, I have already created this plot, so I just want to show you. That's what you get basically for topography. That's one of the input files one of the input fields that you will need to enter. Unfortunately, I wanted to show you more, but it looks like in my current setup, I cannot click anything in this window, so I will return back to the slides. We can discuss it more once we discuss Mars tomorrow. So I'll just, sorry, I'll just get back to the slideshow. Okay, so this was topo file. I just wanted to show you more. So basically it contains all the fields that you need to specify a topography. Topo OC is pretty much the same for ocean topography, a little more simple. Basically, you specify bathymetry of your ocean. RVR is river directions file. So if you want rivers to flow through your land surface and take water from one cell to another, like from basically water goes from lake to lake. So you have to specify this file, and that basically this file basically tells for each cell which is cell will be downhill to which cell the water will flow. And in Planet 2 branch, you will also be able to just use topography file for rivers flow, but on Planet 1, in Planet 1 branch that is currently released, you still have to specify this file. If you omit it, your model will still work, but there will be no river flow. So all lakes which form in your cells, they will just stay in the same cell, and the water will not go anywhere. Name river file, it's again optional file, but you can specify in this file for each river, you can specify river mouse and give it the name, and you will get some nice diagnostics at the end of PRT file at the end of the year, like how much flow did you get from that river. Variable lake is a parameter which you nearly always should be setting to 1. It's variable underscore LK. That basically means that your lakes are allowed to change their area. If for some reason you don't want lakes to change their area, you can set this parameter to 0, and the lakes will be just frozen to the size as you specified them in topo file. Or if you didn't specify them in topo file, then I guess they will not form, but that probably will be slightly contradictory. So you have to either specify them in topo file or allow them to basically to grow. Otherwise, you may even crash against the model. Yeah, OIC file is needed, as the Kostas already explained, if you have ocean, so that you need ocean initial conditions. Gel melt is the file which specifies, it's kind of a weird file. It actually specifies where your icebergs go. This is a problem that because the model doesn't model basically ice flow from the glaciers to ocean explicitly. For example, in Antarctica, we don't have algorithm which will just break ice from the ice shell and put it into the ocean. So you have to specify it with this file, and basically what it does, it takes extra snow or extra ice from your land ice and put into ocean where you said it should go. And this is partially controlled by this next parameter, VSN max, which basically tells how much snow you allow to accumulate at the land. So everything above that height will go to gel melt specified areas in the ocean. So this basically serves two things. First, we want actually to basically remove ice where we are supposed to remove it, like Antarctica to the ocean, but also in some cells, just sometimes because of model imperfections, sometimes, well, it really happens, I guess, in simulated climate that you accumulate snow indefinitely, and often you don't want to do this, I don't know, just because you don't want to deplete your ocean or for some other reasons. So you usually set it to a certain fixed amount so that everything above it goes to the ocean. But normally, if you have land planet, you should set this, you should disable this parameter by setting it to 0 so that you actually allow accumulate as much snow as model wants to accumulate. Otherwise, you will be just basically, you will be not conserving water because the water will be removed to glaciers, to icebergs, which are never actually put into the ocean because ocean doesn't exist.
Igor, isn't this 2 meters by default?
Yeah, I think it's 2 meters. I don't know who put 5 meters on the slide.
Probably a typo.
Yeah, probably. But it's 2 meters, the default value.
As far as I remember, like on most branches, it is 2 meters by default.
Yeah.
Yeah.
Should also mention the reason for this is that we don't have a dynamic land ice model, as Igor was saying in a roundabout way.
Yes, I guess that's part what I call the imperfection of the model. Yes, so basically snow, once it's accumulated, if it cannot melt and or sublimate, it wouldn't go anywhere. It will just stay in the cell. And sometimes we want to remove it just because it's physically it's not very meaningful. Like you don't want to.
Yeah, literally you can get grid cells with thousands of meters of snow if you're not careful, and your sea level will start dropping. And those are diagnostics you can actually see in the model, which maybe we'll talk about a little bit later if we have time.
Yeah. Okay, so next slide. Okay, this is a different slide. This is a slide about orbital parameters. That's the stuff that goes to your run deck. So basically, whenever you specify non-Earth planet, that's what you have to specify in your run deck. So you specify planet name, and that part actually is connected to the code. So the planet name which you specify actually has to be also pre-configured in the source code. I will explain just a few minutes later what it is. So that should link your run deck to the source code. Then eccentricity, you just specify the number in the run deck. We'll have examples tomorrow how it's done. So you can specify obliquity of the orbit. Then for the calendar, you specify, basically for the orbit, you specify sidereal orbital period in seconds and sidereal rotation period in seconds. And that's pretty much defines your orbit. And then quantize year length, it's a logical parameter which usually have to set to true, which is true. By the way, true is one in run deck language. So anyway, you have to set it to 1, so that that basically means that you want, I think, integer number of days per orbit. So that's kind of better for diagnostics, and that will massage your time stepping or orbital period slightly to get integer number of calendar days per orbit.
Yeah, let me just mention something quickly, Igor, that just as an aside, anything that's not set here will default to Earth values, basically. So if you forget to set the obliquity, it'll default to Earth obliquity. If you forget eccentricity, it'll default to Earth. If you forget any of these sidereal parameters, it'll default to Earth. So make sure if you have a funny planetary system, you define all of these quantities explicitly, otherwise you'll end up with a funny run.
Yeah, it's a good idea to take some of our examples for definitely non-Earth run and basically specify every variable that is specified in the run deck with respect related to calendar to something that you want to have. So then for atmospheric components, it's also the way how it's specified is inherited from Earth. So a lot of gases are specified as greenhouse gases, and they are specified in GHG input file. So there are two options actually to specify it. I think I would recommend just to use GHG file and specify explicitly or amount of greenhouse gases that you want to have just in parts per million. But you can also specify multipliers in the run deck. These are the parameters: O2x, CO2x, and N2OX. So if you specify one of these parameters, for example, equal to 2, then the value specified in GHG file will be multiplied by 2. And that's what will be the value that will be used by the model, at least for radiation purposes. So better specify it, in my opinion, better specify it just in GHG file and don't use this.
Yeah, sorry, there's also a typo here. O2x is not specified in the GHG file, as Igor knows. That should probably be CH4x.
Yeah, I guess it's not a greenhouse gas.
Not a greenhouse gas, exactly. So that's a typo on our fault.
Yeah. So basically, atmospheric constituents you specify partially here, and now since we are already to the string about like planet params file. So this is the file which is very important. Basically, this is probably the only file that you need to modify. It's model shared planet params._mod. And this file will contain sections for different planets, which you specify by planet name. And for each of the planets, you have to specify certain things like surface pressure, one of them, and also you specify basically the atmospheric components for different gases. And you explicitly say, basically set for everything that may be present on Earth to 0, just to zero out stuff that you don't need. We will probably have examples tomorrow, so I think I will not show you this file right now. Maybe we can look at it later today. So, but remember
one thing to mention about the GHG file, which is important, sorry, I'm going backwards, is that it has several lines. It can have several lines in there, one per year. And the line that will be used is the one line defined by master year, as I was saying earlier today.
Yes. Also, if your master year and the year specified in GHG file are completely different, or there is only one line, it will be used anyway. So whenever we read GHG file, we are trying to find the line closest to the year specified by master year, or for transient runs, basically to current year. So even if those don't coincide, usually if there is one line, it will be used. If there are several lines, then there will be used the one which is closer to the year that the model is using. Then this planet underscore S0 is important parameters, because that's basically your solar constant. So by default, again, it defaults to Earth's solar constant, but whenever you use anything other than modern Earth, you have to set this parameter to the solar constant that you want to use. There is another way to specify it. I don't know. I know not everybody likes it, but actually you can skip this parameter and specify the distance from the sun in AUs, and then Earth constant will be scaled with respect to that distance from the sun. The only place where we are using it, as I know, is for Mars, in Mars Rundeck, because it's just too convenient to set for modern Mars, just to set the distance from the star and basically get the right solar constant. But for everything else, you shouldn't set the distance, but you should set this planet as 0 in watts.
So Igor, maybe we could look at the planet params now. I mean, we have plenty of time, so maybe it's worth it if you have the ability to do it.
Yeah.
Because it's so important, I think, while we're talking about it.
Yeah, just this.
Isn't this something that Chris will cover tomorrow?
It'll be, well, he'll show for one configuration, but he won't explain every detail of it the way that Igor can.
Yeah, let me see if I can easily play this. Oops. No, sorry. Okay. It's not the computer that I'm usually using for my work, so I don't even have graphic Emacs installed. So, well, anyway, this is the file. Unfortunately, there is no like nice coloration, but basically, the sections which are important for you are these sections which are specified for different file names, for different planet names. So like, let me see, for example, this section, like Mars, oops, yeah. Can you see clearly this part, or should I make font bigger?
It's fine.
No, it looks good, I think.
Okay, so this is basically, whenever you create new planet, this is the only thing that you need to do. You have to create new section like that in this file. So basically you give it the name, then you give it, like you repeat this name so that it's inside the structure, and that's the name that we'll be using in the Rundeck when I was talking about planet name. So then you specify here gravity. So for Mars, it's like 3 times less than Earth. You specify radius of the planet in meters. You specify molecular weight of your air or whatever gas it is. So Mars is basically, yeah, we are using pure CO2. It's slightly less pure in reality, but yeah, so we set to 44. SRAT is a ratio of CP to CV, or vice versa. Yeah, I guess CP to CV. So
CP to CV.
yeah, CP to CV for current gas. So that's important that basically when you change atmospheric components, you have to specify this. It's basically CO2 is 3-atom molecule, so it's different from N2 in the air. Though I guess for CO2 it's not different that much because it's kind of, I guess the molecule is nearly linear in CO2. Anyway, PSF is your surface pressure in millibars. So here we set it to Mars, so it's about 6 millibars. So it's average. It's mean surface pressure over the entire planet that we are setting. So depending on topography, somewhere it will be bigger, somewhere it will be lower. P-top is funny parameter. So basically what it tells, it's not what it thinks, one might think. It's not the top of the atmosphere. It's actually the pressure where sigma coordinate system changes to constant pressure coordinate system. If you know what it is, basically it's just a transition between like different representations of vertical coordinate, and it's supposed to happen smooth, but basically above this, one important thing is that above this pressure, there could be no topography features. It should be actually far above topography features. For example, on Mars, you have Olympus Mons, which is very hot mountain, very high mountain, and this P-top should be above it. And often if you have very high topography, your model may crash over that topography, and that often means that you have to raise this P-top, I mean, make it smaller so that the transition between two coordinate systems happens upper in the atmosphere. So this is kind of like tuning parameter. So for Earth, it is set where, yes, this is normal Earth, yeah. So for Earth, it is set to 150 millibars, and normal rule of thumb, just scale it the same way. So it's approximately like, I don't know what is 1/8, or like if you have 1000 millibars surface pressure, then it should be 150 millibars. So if you have 10 millibars pressure, then it should be 15 millibars. So basically just whenever you create new planet, if you don't know where to set it, just scale it the same way it is done for Earth. Okay, and at the bottom of this structure, basically you set just different amounts of gases. Again, I think it's in ppms. Let me see what is done for Earth. Oh no, here it's not in ppms. Here it's in fractions. So here it's basically just fractions of one. So it's 78% of N2 for Earth, 21% O2 for Earth again, and for Mars we set all of those to 0 because CO2 we specify as greenhouse gas. So I should oops, where
and if you go to the top, Igor, you can show them some other options. Yeah. So there's H2 also as a possibility to set here.
Yeah,
as
yeah.
well.
Okay, so these are the defaults which are specified at the top. Yeah.
Yeah.
So again, I guess try to look at our examples from publications what we are using. But yeah, pretty much I guess those are all gases that can be specified. Yeah, I guess CH4 is specified in the GHG file. That's probably all you need to know about this file. So just basically create your own section here if you want to create your own planet. Okay, so I guess this slide also mentions constant, or maybe we shouldn't speak about constants. I don't know, Michael or Kostas, should we discuss any other files while we are here, or suggest?
Well, I don't think you need to discuss the constants one, because
the constants are constant, basically.
Yeah, it's straightforward.
I don't think people will change that. It's important, but it's okay. So I'll just continue the slides, I guess. Then. So this basically was discussed. Okay, single column model. I'm not actually sure if Planet 1 handles it properly.
There is a single column version. It's just kind of a beta. We've used it a few times, but not extensively.
Yeah, I probably wouldn't recommend. I mean, people use it, but it's probably not very user-friendly at the moment. So, but yes,
no,
such option.
It's not user-friendly.
Such option exists, so you may try to contact us if you really absolutely need it. But in Planet 2, it will be, I think, standard option. There will be run deck, so you will be able just to use it. So basically, what the single column model does, it just, as the title describes, it just runs the model for one single basically GCM cell, and you specify. Actually, it would usually, I guess you want to run one single column option for atmospheric part, so you specify everything that happens on the land, and basically drive atmospheric part together with radiation to see what happens, like to clouds, and yes, how much radiation you get at the surface. Depends on which questions you want to ask. Yeah, and it will be quick, of course. So probably nothing more here. Okay, the event of crash. You will see a lot of crashes once you switch from Earth to non-Earth configuration. So this is a document which you can look at, which will basically tell you what to do in most standard cases. I don't know, Mike, do you want to look at this document right now, or is it?
Maybe not. We can wait for.
Yeah, maybe
time,
during question and answers. So basically, yeah, it's if you don't know what to do, the first thing to do is to look at this document and see if the crash that you are getting was already described. And that would mean that you will need to change certain run deck parameters. And sometimes you would have to go to the code and change a couple lines in the code and recompile.
Or you might get lucky and you can just change the I file. You never know. It depends on what it is.
Yeah, but basically you get crashes often because like the thickness of your atmosphere is different. So if you have very thin atmosphere, usually the speeds of of winds become faster, so you violate stability conditions, or again, if your atmospheric layers are very thin, then radiation may overheat those layers on single time step, so you have to go to smaller time step and call radiation more often. So things like that usually crash the model, or your ocean freezes to the bottom, and our model doesn't allow you to freeze the ocean to the bottom, so you have to do something with that. So usually it's stuff like that. Most often it's some kind of instability in the model, and just a question to figure out what it is. And mostly, basically, you just cure it with brute force methods. So you have to go to shorter time steps, like in dynamics or in physics, and increase atmospheric drag, which basically just slows your atmospheric winds at the top of the atmosphere and stuff like that. So what is next? Okay, so this is basically the model output. That's what you get. So in your run directory, when you're running the model, these are the files that you'll be getting. .prt file is basically kitchen sink. Everything that written with print statements in the model will go to this file. So it's kind of messy and it's very big, but if you know what you're looking for, then you can find it there. And most importantly, when your model crashes, usually the end of this file will kind of describe your crash. Normally it will give you like the reason the model has crashed, and sometimes certain diagnostics before the crash, so you can see what was going on. It also contains budget pages. GCM people usually like to, at least like old generation of GCM people like to look at those budget pages, which basically just give you mean numbers for the entire planet, like surface temperature, air temperature, ground temperature, humidity, stuff like that, evaporation, precipitation. So just to give you general idea what's going on. But they're also tuned. I mean, printout is tuned for Earth parameters. So sometimes you may just get zeros because the scale of parameters will be different for your planet. But if it's close to Earth, then you'll get something meaningful. This month, year, and ACC run ID netcdf files are accumulated diagnostics that your model will be printing, writing out. Those are not human readable files, and they need to be post-processed to become usable. This is basically just a quick way for model to dump the important data, and you should never actually look at these files with any viewers. You will not see anything interesting there. But yeah, I guess we will describe later how to post-process those files. So other files that are written are RSF files. They will have RSF letters in their names, and those are restart files. They basically save the entire state of your model, so you can use those and to restart identical run from those files. Usually these files just needed to basically to start new runs from the state your model was in. For example, you do some spin-ups, so you run the model for 1,000 years to get equilibrium for certain for a certain planet, and then you want to do some experiment by changing something. So you save this restart file and then start completely different run, but say like use this restart file as an initial conditions file, and you specify this again in the run deck. So you just point the file which is called AIC, which is atmospheric initial conditions, to this RSF file, and the model will restart from that file. This is KRSF parameter, which basically specifies how often you want to save this model. If you don't specify it at all, the model will do something reasonable. I think it will save it once every orbit, or once every 10 orbits. I don't remember exactly. It's different on different branches. Then there are files called fort1 or 2.nc. Those are basically checkpoint files. They're similar to RSF files, except RSF files don't contain diagnostics, because diagnostics are reinitialized on at the beginning of every month. But this fort1 and fort2 file contain everything. So it's basically like memory dump of your model. And if your model crashes, or if you stop it with SWE, or
yeah, SSW. These are the checkpoint files I was mentioning earlier.
So I guess Kostas already described them. So basically, they're always created while the model is running, and also such file is created when you stop the model, if you stop it gracefully. And the model by default will restart from the latest of these files that was created, and the restart is supposed to be identical. So typically when you do a long model run, say you write these files periodically, and when your model stops, you can always just like, because it is killed by the system, that because you run out of time, and when you restart it, it will restart from this file. So again, NDisk specifies how often you want it to be written.
Okay, Igor, I think I promised a break after 45 minutes, I think. So
okay, maybe.
Why don't we talk about this is kind of post-processing, so we can take a break, I think.
Okay, yes.
I think it's almost done.
Well, there's a couple more slides.
Yeah, there are.
Which describe. Okay, we can break, and then we'll just switch to ACC files, because I think that's what it is. Yeah.
So let's take a 15-minute break. Everybody can use the bathroom or get a drink, and we'll come back, and Igor will finish up the post-processing, and then it'll just be question and answer session, which is already going on in the chat window, from what I can tell.
Yes, the chat window is active, and I'll be staying here. So if you want to continue doing it on the chat window or even live, just go ahead.
Okay, so we'll be back Igor will start up again at 8, or not 8, sorry, at 2, not 8.
8 is my time.
Okay.
Yeah.
Yes.
I'll just say in the chat window, I added the Google Doc on creating a new planet that goes through those examples in that Igor did with changing the molecular weights and the atmospheric constituents and such.
Yeah, Chris will cover this tomorrow towards the end of the day, is how to create a new planet.
Yeah, we will also look, I think, in more details how Mars run deck is created. So we will kind of see a specific example tomorrow. Can I mute myself when I'm sharing? I don't see.
Yes, of course.
I cannot click on anything, or maybe. Oh, I don't see.
You're still sharing.
Yeah, I guess I have to unshare. Well, I'll unshare and I'll share them again. Because otherwise, I don't see interface which would allow me.
Oh yes, yes. It minimizes most of the things when you are sharing.